Hey everyone, I'm Stan, and in today's session, I'll talk about the interactions of radiation with matter. In this talk, we'll cover the basics of interactions of photons and electrons with matter, the concept of linear attenuation, consideration for polychromatic spectra, and practical imaging considerations. The photoelectric effect was first observed in 1887, but this was quite puzzling. This effect was the observation that electrons are emitted from materials that are exposed to electromagnetic radiation. But for one, classical wave theory could not explain why no electrons were being emitted below a certain frequency, regardless of intensity. Secondly, the energy of electrons depended on the frequency of incident light and not the intensity. In 1905, Einstein proposed that light consists of photons with energy proportional to frequency, which explained the photoelectric effect and provided foundational evidence for quantum mechanics. This intellectual leap forward earned him the Nobel Prize in Physics in 1921. In the photoelectric effect, an incoming photon, depicted here, interacts with an inner shell electron. The photon is completely absorbed, and the electron is emitted as a photoelectron. And then the vacancy left by the emitted electron is filled by an outer electron that transitions down to this lower energy level, and a characteristic X-ray is emitted. In 1914, the Frank Hertz experiment was performed, and is now a classic undergrad physics lab experiment. In this experiment, electrons were accelerated through mercury gas. As expected, with higher accelerating voltages, current increases. However, once certain voltages are reached, the current suddenly drops. Now, these drops are explained by the existence of excited states in mercury, which confirm the prediction of quantum mechanics that electrons only exist in discrete quantized states. And this experiment also earned the Nobel Prize in Physics in 1925. Quantum mechanics is also corroborated by the existence of characteristic X-rays. Now, we've all seen objects glow red or even blue when heated. Well, hot gases, like the sun, emit light in an emission spectrum. So, when using a prism, for example, to separate the emitted spectrum, we observe discrete lines. And these correspond to characteristic radiation, and each element has its own set of lines corresponding to its differences in energy levels. The process for generating characteristic X-rays begins with an atom being excited or ionized. Now, this results in a vacancy in an inner shell at a low energy level. Now, an electron from an outer shell transitions to the inner shell vacancy. When this transition happens, a photon is emitted with energy equal to the difference in energies between the two states. Since atomic energy levels are discrete, so is the emitted photon energy, hence the term characteristic. So, the next interaction of interest is Compton scattering. In this case, classical wave theory of light couldn't explain the results of high-energy photon interactions with matter. X-ray experiments showed unexpected changes in wavelength after interacting with electrons. Arthur Compton observed that X-rays scattered off electrons in graphite had longer wavelengths than the incident beam, with a shift that depended on the scattering angle. Compton proposed that light behaves like a photon with momentum and derived the Compton equation, explaining this wavelength shift. And for this, he won the Nobel Prize in Physics. So, in Compton scattering, the incoming photon interacts with an outer shell, loosely bound electron. The photon is scattered with a reduced energy, and the electron is freed from the atom, imparting some kinetic energy. Energy is conserved, as well as momentum, with the shift in photon wavelength being dependent on the scattering angle. Now, Compton was able to predict the change in energy of a photon as a function of scattering angle. But to go a bit further, the Klein-Nishina formula describes the differential cross-section, which is proportional to the probability, of Compton scattering as a function of energy and angle, with the formula given here, where R0 is the classical electron radius, E prime is the scattered photon energy, and theta is the scattering angle. This equation was derived by Oscar Klein and Yoshio Nishina in 1928, and this agreed really well with scattering experiments, where Thomson's predictions deviated from measurements. You can see here the Klein-Nishina distribution, also known as the peanut graph, showing cross-sections as a function of angle and incident energy. For example, you can see that high-energy photons are much more likely to be scattered in a forward direction, as compared to lower-energy photons, which are essentially equally likely to be backscattered as they are to scatter at small angles forward. As a next interaction, we have Rayleigh scattering. Now, in 1871, Lord Rayleigh explained the origin of the blue colour of the sky, essentially with the equation that the intensity of scattered radiation is inversely proportional to the fourth power of wavelength. So, this effect was explained as being due to the electromagnetic scattering of sunlight by molecules in the atmosphere. The sky is blue because the blue end of the visible spectrum, with a lower wavelength, scatters more than the rest of the visible light spectrum. Thus, the intensity of light incident on Earth, due to scattering, is dominated by the blue end of the spectrum. Rayleigh scattering is the elastic scattering of photons by bound electrons. Next up, we have Thomson scattering. Now, Joseph John Thomson was born in suburban Manchester in England in 1856 and lived with his family in Plymouth Grove. He was born in an era where there were no bicycles, no motor cars, no telephones, no wireless radio, and no electric light. A humble man of working class roots, Thomson went on to become one of the most influential physicists of the late 19th century. And based on the image hung in this room, he must have had good taste. Now, in the earlier 20th century, J.J. Thomson developed a classical model to explain how electromagnetic waves scatter off free electrons, and this was before quantum mechanics. Thomson scattering is the scattering of photons by free electrons, and it's the low energy limit of Compton scattering, where the energy of photons is much less than the binding energy of electrons. And coherent scattering is just a term that combines Rayleigh scattering and Thomson scattering. Now, in coherent scattering, a low energy photon interacts with bound or free electrons. There's no energy transfer or ionization, only a change in direction of the photon. This interaction is typically negligible in radiology, as it's only important at lower energies such as below 25 kiloelectron volts. Coherent scattering causes no energy deposition and thus no dose, and it's dependent on material and energy. Another important process is known as pair production. Einstein laid the groundwork with mass energy equivalence in 1907. Paul Dirac developed a relativistic quantum theory of the electron, which predicted the existence of antimatter in 1928. Carl Anderson observed tracks of a positively charged electron, now known as the positron, while he was studying cosmic rays with a cloud chamber. Carl Anderson won the Nobel Prize in Physics in 1936 for this discovery, which validated pair production as a real physical process. Now, in pair production, the photon energy is required to be at least 1.022 MeV, i.e. at least twice the electron rest mass energy. Now, the incoming high-energy photon interacts with the nucleus and converts into an electron and a positron, which conserve momentum and energy. The positron subsequently annihilates with another electron to produce two collinear 511 keV photons. As an extra interaction, we present photodisintegration. This is the process where a high-energy photon of at least 10 megaelectronvolts is absorbed by a nucleus, which then becomes excited and ejects a nuclear particle, such as a neutron, proton, or alpha particle. This process was experimentally observed by James Chadwick and Maurice Goldhaber in 1934. However, this interaction is not important in diagnostic imaging, as the binding energies of nuclei are of the order of megaelectronvolts. So this process is much more important in radiation oncology medical physics. Now, we've covered a variety of different interaction processes, but if we take a step back and recall, we have photoelectric absorption, we have Compton scattering, and pair production as our three most important interactions. Now, the probability of each interaction is dependent on both the material being traversed and the energy of incident photons. Now, photoelectric absorption follows a cubic relationship with proton number and inversely with the energy of the incoming photon, whilst Compton scattering just has a linear relationship with proton number independent of energy, while pair production is proportional to the square of the atomic number, with this diagram essentially showing this for germanium and silicon. Now, in radiology, lower energy and higher atomic number shifts probabilities such that photoelectric absorption is more likely. Now, we know that the probability of each interaction depends on both the photon energy and the atomic number of the material. So let's say we have an atomic number of 20. Now, for energies up to about 100 kiloelectronvolts, photoelectric absorption is the most probable interaction. Now, going at energies beyond, so from about 100 kiloelectronvolts up to 10 megaelectronvolts, Compton scattering is the most likely interaction. Now, at those energies beyond 10 megaelectronvolts, this is where pair production would be the dominant process. So what these lines tell us is energies and atomic numbers at which photoelectric effect and Compton scattering are equally likely, or where Compton scattering and pair production are equally likely processes. Now, in radiology, Compton scattering and photoelectric absorption are the most important interactions. So now, instead of talking about interactions of photons with matter, we'll talk about the interactions of electrons with matter. Now, J.J. Thomson in 1897 discovered the electron using cathode ray tubes. Early 20th century studies revealed that electrons can ionize atoms and cause excitations, which, as we know, result in characteristic radiation. Bremsstrahlung radiation, meaning in German breaking radiation, is another possible interaction of electrons, which was coined by Arnold Sommerfeld in 1909. Now, the development of radiation therapy and diagnostic imaging was built upon the understanding of electron-matter interactions, and it is also the basis for high-resolution scanning electron microscopy, as shown here, which can resolve objects of the order of nanometers. Now, the first type of electron interaction is collisional. So, for example, an incoming electron can cause excitation. Now, the electron imparts some of its kinetic energy to an inner shell electron, which transitions to a higher energy level. Now, as we know, when the atom de-excites, so this electron returns to its ground state, low energy photons in the visible or ultraviolet spectrum are emitted. Alternatively, an incoming electron can cause ionization, where the inner shell electron is ejected, which produces an ion pair. Now, this also results in de-excitation. The next type of electron interaction is known as radiative. So, an incoming electron can result in Bremsstrahlung. In this case, the electron is deflected by the electromagnetic field of the nucleus, as shown in the dynamic visualization. So, as the free electron is accelerated by the field of the nucleus, its lost kinetic energy is converted into radiation. Now, this radiation is emitted as a continuous spectrum. And recall, this is a radiative interaction. And this is actually the process by which photons are produced in an X-ray tube. Now, as a bit of an aside, many of the greatest scientists that made important discoveries in physics have something in common. Rutherford, Moseley, Bragg, Geiger, Marsden, Bohr, Chadwick, Darwin, Game, Novoselov. The Department of Physics and Astronomy at the University of Manchester has been a home to 11 Nobel Prize winners. Now, this is a very old photograph of a place known as Brailsford Road, which back in my poor and miserable undergrad days, I used to live on. Now, moving on from the basic interactions of radiation with matter, we introduce a concept called linear attenuation. Now, the linear attenuation coefficient is a constant that describes the fraction of attenuated incident photons in a monoenergetic beam per unit thickness of a uniform material. So linear attenuation is the result of all possible interactions. So photoelectric absorption, Compton scattering, coherent scattering, and pair production. The concept of linear attenuation characterizes how easily a volume of material is penetrated by a beam of photons. And it's essentially a macroscopic approximation. So it refers to the intensity of a beam that's composed of a lot of photons. Now, also central to attenuation is the concept of half-value layers. So a half-value layer is defined as the thickness of material that's required to reduce the intensity of an X-ray beam to half of its original value, and is given by the equation shown here. Now, this is most accurately measured under narrow beam geometry, as broad beam setups allow scatter to reach the detector, leading to an underestimation of attenuation unless corrected. So this HVL serves as a surrogate measure of beam quality or X-ray spectrum penetrability. And as an X-ray passes through material, beam hardening occurs, as we know that lower energy photons are preferentially absorbed, which effectively increases the average energy of remaining photons. So each subsequent layer has a larger HVL than the previous one. The 10th value layer is the thickness of a material required to reduce the intensity of an X-ray beam to a tenth of its original value. So it's similar to half-value layer, but represents a greater thickness of material that's needed to reduce the beam intensity even further, as you can see from the equation. So this also serves as a surrogate measure of beam quality or X-ray spectrum penetrability, and like HVL, TVL is important and common in X-ray shielding design, where shielding can be conceived in terms of TVLs that are required to reduce dose rates to certain levels for radiation protection purposes. Now, to discuss a bit more these concepts of narrow and broad beam geometries, narrow beam geometry uses tight collimation for the source and detector. This provides accurate measurements of the linear attenuation coefficient and is an ideal setup for measurements of HVL, TVL, and so on. So the measured attenuation reflects the primary beam attenuation, whereas in the broad beam geometry, with a larger field size, the detector accepts a lot more scattered photons. So this simulates realistic clinical conditions, such as imaging a patient, but more photons reach the detector, which are scattered, which leads to an underestimation of the linear attenuation coefficient. Now, another concept very close to linear attenuation is mass attenuation coefficient. And this is very simply defined as the linear attenuation coefficient divided by the material density. So this measure is useful for comparing attenuation properties independently of density. And this concept's introduced to standardize attenuation across materials. And mass attenuation is additive for compound materials, and so it's a very important concept for dosimetry and shielding calculations. Now, what we have here is some example mass attenuation coefficients for different materials at a range of energies. Now, the difference in attenuation coefficients of different materials in diagnostic imaging is what enables contrast. Since the different materials, let's say at 30 kiloelectron volts, have different attenuation coefficients, we can generate meaningful images. For example, the mass attenuation coefficient of fat and soft tissue at 30 keV, it's very similar. So these materials will hardly be distinguishable, whereas they would be distinguishable from bone and even more from iodine and lead. Now, circling back to our original definition of linear attenuation coefficient, we stated that this was for a monochromatic beam, so a beam composed of photons of a single energy. However, real X-ray beams are polychromatic. They have a broader energy spectrum. And since the probabilities of interaction are energy dependent, the attenuation of a real X-ray beam has to be modeled using an energy-dependent attenuation coefficient and spectrum, as given here, with the attenuation coefficients as a function of energy for different plastic materials being shown in this diagram. Now, the differential attenuation as a function of energy, as we know, results in beam hardening. And this has really important considerations for CT calibration curves, material decomposition algorithms, and image contrast and artifact correction. Now, we've discussed narrow and broad beam geometries. Now, in a more clinical focus, in radiology, scattering interactions degrade image quality. So, a larger field results in a greater proportion of photons scattered into the detector relative to a narrow beam. So, this results in increased noise and reduced image contrast. Secondly, an increased patient thickness results in a higher proportion of scattered photons reaching the detector. And due to beam hardening, more scatter is produced in deeper tissues. So this results in the need for a higher radiation dose to maintain image quality. So the takeaway from this is that field size should be optimized by using collimation. So to summarize, the general factors that affect attenuation include the photon energy, the atomic number and density and thickness of material being penetrated, as well as the radiation type and beam characteristics, as well as filtration. Now, these are all important considerations when we think about image quality, radiation dose, radiation safety and protection, and the general optimization that a medical physicist should be doing. So, to summarize, in this video, we've learned about different types of interactions of photons and electrons with matter. We've learned that attenuation is useful for describing the macroscopic effect of all these interactions in an X-ray beam. And we've learned that field size, patient thickness, material properties, and beam characteristics influence image quality and radiation dose. And all of this matters because these principles underpin medical imaging, radiation therapy, and radiation protection. And understanding these mechanisms allows us to improve diagnostic accuracy, optimize treatment planning, and to minimize radiation exposure. Thank you for listening. I hope this video was useful, and as usual, if you have any questions, please get in touch.